Welcome back. We're still on day 4. We're looking at arc lengths and circle sectors in our Unit 9A, Circles Part 1. We talked about arc length and how that differs from arc measurement. Your arc measurement will never be bigger than 360 degrees. It's always going to be somewhere between 0 and 360, because if you have a small circle or a big circle, you always have 360 degrees. Okay? And then we talked about the circumference, the length around a circle, will be different depending on if you have a big circle or if you have a little circle. If I have to walk around this big circle, I'm walking a much further distance than if I'm walking around the little circle. Okay? And so we use our circumference to find the length of that arc. And then we talked about what happens if you're not going all the way around the circle and you just want to find a partial arc around the circle. And we kind of developed a little formula where we said you can find the length of part way around the circle of a minor arc or a major arc, or even a semicircle, using the measure of the arc over 360, because that's going to tell you how much of the circle, what fractional part of the circle do you want, and then you multiply that by the circumference. So the measure of the arc divided by 360 times 2 pi r will find our arc length. Okay? Here it's asking me, well, what fractional part of the whole circle are the following measures? So the fractional parts, let's see, let's try that. 120 out of 360, what would that reduce to? Okay, so we can figure out what goes into everything. We can take our zeros and they'll cancel out, right? So it's really just 12 over 36, which are both divisible by 6. 6 goes into 12 2 times. And 6 goes into 36 6 times. So it looks like, oh, I could have put 12 into both, right? Because 2 6 still reduces. This is 1/3. So 120 degrees around the circle is 1/3 of the circle. Okay? When I look at the next one, 270 degrees, if I put that over 360 and try to think about what goes into both of those numbers, well, 9 goes, I'm going to not think about the zeros. 9 goes into 27 and 9 goes into 36. So 9 goes into 27 3 times. 9 goes into 36 4 times. And that can't be reduced any further. That's as low as that can go. Okay? 144 over 360. Well, I already remember over here 12 goes into 360. And I know 12 goes into 144. So 12 goes into 144 12 times. And 12 goes into 360, I want to say 30 times. 360 divided by 12 is 30. Well, those are both even, so I can definitely go by something even bigger than that. So let's see. Actually, 6 again, right? 6 goes into 12, 6 goes into 30. 6 goes into 12 2 times. And 6 goes into 30 5 times. So 2/5. 2/5 is 144 degrees, is 2/5 around the circle. And then 300, oh, I should have changed colors there. 300 divided by 360. Let's see, so that's going to be like 30 divided by 36. 6 goes into both 30 and 36. 6 goes into 35 times, and 6 goes into 36 6 times. So, and that doesn't reduce any further. So 5 6. So 120 degrees is 1/3 of the circle. 270 degrees is 3/4 of the circle. 144 degrees is 2/5 of the circle. And 300 degrees is 5/6 of the circle. Okay? All right, so now my next question says, if the circles below have a radius of 48 millimeters, what would be the exact indicated arc lengths? Okay? So all of them have a radius of 48 millimeters. Okay? And then look at my angles. I've got 120, I've got 90 degrees, 144 degrees, and 60 degrees. Okay? So, and I want to find the length of the indicated arcs. Okay, so the first thing I'm going to do is, I know that we had this formula that we kind of developed in the last video that says the fractional part, the measure of the arc over 360, is equal to 2 pi r. So all of these, I'm going to need my circumference, because remember we did the fractional part times the circumference. The fractional part times the circumference. Which means all of these, since they all have the same radius, they're all going to have the same circumference. So let's figure out, well, what are those circumferences? Okay, so I'm going to figure out what the circumference of these circles are. 2 pi r. My circumference is 2 times pi times the radius, which is 48. And so my circumference for each of these, excuse me, my circumference is 2 times 48, which is 96 pi. Sorry about that, got a little croupy. All right, so then I'm going to use that formula that says the fractional part over 3, or the fractional part times the circumference. So my first arc length is AD, so I know I'm starting at A and I'm ending at D, and since there's only 2 letters, I'm going the short distance. So that is 120 degrees out of 360, which magically I already happen to do right there. I know that's 1/3 of the circle. So 1/3 of the circle, and I know my circle, we already did the circumference, my circle is 96 pi. So I'm going to do 1/3 times 96, and since it wants the exact answer, I'm not going to use the pi. So I'm going to do 1/3 of 96, which is going to be 96 divided by 3, and that's 32. And then since I didn't factor in the pi when I did the 1/3, I just did 1/3 of just the 96. I haven't used the pi yet. I need to still write it down here. That is the length of just the blue arc, 32 pi, when the whole circle is 96 pi. Okay, let's look at the next one, number 6, or the next one on number 6. The length of arc CET. So I see that 90 degrees there, and it's real tempting to go, oh, that's 1/4 of the circle, right? But be careful, if I want arc CET, that means I'm starting at C, and I'm ending at T, and I have to go through E. So it's not really the 90 degrees that I want, right? It's this back side, which is the 360, the whole circle, minus that 90 degrees. So that is 270 degrees. So it's 270 degrees out of the 360. Oh, which I already did there, 3/4. So I want 3/4 of the whole circle. The whole circle we found to be 96 pi. And you notice how I kind of wrote it up? When I have a number that's got a number on the top and a number on the bottom, I kind of like think of this as 96 over 1, so I can multiply this way. And I can do 3 times 96 is 288 over 4 times 1. And then I just have to reduce that fraction, and I think it divides evenly by 4. 288 divided by 4 is 72. So it does. 72 pi is my exact answer for this one. Okay, so it's normally 96 pi all the way around. If we only go 3/4 the way around, it's 72 pi. All right, when I look at the next one, the length of HS. So I'm starting at H, I'm ending at S, and since there's not a third letter, I'm going the short way around, which is 144 degrees out of the 360, which I happen to already do right here. I know that is 2/5 of my whole circle, and my whole circle is 96 pi. And again, since I have a fraction that has not weird numbers, but not ones, not a 1 on top like I had over here. Since I have a fraction with numbers other than 1, I'm going to write this as 96 over 1 times pi. Okay, so that's going to get me to 96 times 2 is, oops, I divided by 2. 96 times 2 is 192 over 5 pi. Now, 192 is not divisible evenly by 5, and there's nothing that goes into 5 because 5 is a prime number. So I'm going to leave this exactly like this because that 192 over 5, that does not reduce. And it wants the exact answer, so I'm going to leave it like that. Now, if I do 192 divided by 5 in my calculator and ask for a decimal answer, and I know y'all don't have these calculators, but you do have a regular calculator, so it will do. I'm just doing simple math here. You do get a nice pretty answer of 38.4, and it doesn't keep going if I do divide by 1. You can see it really is just the 38.4. There's not a whole bunch of extra numbers following after it. So that 38.4 is also an exact answer. So you could, if you wanted to, rewrite this as 38.4 pi and still be considered an exact answer because you haven't done any rounding to that problem. If it was some weird like 2/3 and it didn't divide evenly into thirds, although that would, then you'd have a little bit more of an issue with because it wouldn't round correctly. Okay? All right, let's look at this last one. This time we want the length of arc JMH. So I know I see that 60 degrees there, but I want JMH, which means I'm starting at J, I'm ending at H, and I have to go through M. So that means I'm going this long way around. So out of my 360, I used 60 here, which means I've got 300 back here. So I'm really using 300 degrees, which, ta-da, I already used right there. I know that's 5/6 of the circle. And so 5/6 of the whole circle, and my whole circle is 96, which I'm going to write it as over 1 pi. So that way I can just multiply 5 times 96 and then 6 times 1. 5 times 96, I keep dividing, is 480. Over 6 times 1 is just 6, and that that is being multiplied by pi. I believe 480 divided by 6 is a nice pretty number. It is. That turns out to be 80 pi. Okay? Now, kind of the neat thing is you could do this without doing this reduction, and it would still get you to the same answer. If I did my 300 times 96 and my 360 times 1, so if I did this fraction instead of the reduced fraction, I'd still get the same answer. I would just have a bigger fraction here that would still need to be reduced. Okay, so just something to keep in mind. In the next video, we're going to do something very similar to what we're doing here, except instead of looking at just the arc length, we're going to be looking at the whole sector area. So come on back for that video, and I'll see you in the next one. Thanks.